you have to take a look at all the units, okay? So here you can see you have velocity in meters over second, you have the time in seconds. So basically you don't need to do any conversion, okay? So not always you need to do conversion, but sometimes it's going to be necessary, like we did in the class before. So for this exercise, we have, okay, I'm gonna give you this. It says, a racing car reaches a speed of 42 meters over second. It then begins uniform negative acceleration using its parachute and braking system. It means the car was traveling at 42 and then uh, applies the brakes, okay, and begins to slow down. That's what it means. And it says, and comes to rest 5.5 seconds later. So that means that from the moment the car has 42 meters over second until the moment it goes to rest, that happened between 5.5 seconds. Now the problem says, find the distance that the car traveled during braking. So right in the moment the car applies the brakes until it completely stops, I want to know what is the distance, okay, that the car traveled during those two moments. So the first thing that you need to do is you need to get the givens, okay, write the givens. So I know that the car initially was at a certain speed of 42 meters over second. So this is my initial speed. Now here, how do I know that the final velocity is zero? Because the problem tells you comes to rest. Rest means that the object is not moving, okay? So the car was moving at 43 meters over second. So when it says comes to rest, means that the object was moving and then it's not moving anymore. It is now at a complete stop, okay? So what is the key word here? I want to point it out. The word to, okay, is coming from 42 meters over second to rest. So from 42 is initial. The word from represents initial condition. And when it says to rest, so that means after whatever, after 5.5 seconds, then it's not moving. Okay, after 5.5 seconds to apply the brakes, it's not moving. So the keyword here is to. To represents a final condition. Okay, to represents a final condition. So every time you see the word from, represents an initial condition. And when you read the word to, represents a final condition. Always keep that in mind, because in physics, you will always have those two keywords. That tells you how to identify the data. So here is not like you need to add, subtract, divide. No, this is not math class. You have to analyze word problems. Just that. You have the formulas, use the formulas. But using the formulas is not too important. What matters the most is gathering the data from the word problem. So remember this. From means initial condition, while to means a final condition. Now the time given in the problem is 5.5 seconds, and they're asking you to find the distance. Distance and displacement in this kind of problems represent the same thing, okay? Distance. Well, a difference in position. So the formula says that distance, or in this case displacement, is going to be 1/2 the addition of the two velocities times the time. But here what I do is I replace 1/2 by the decimal number 0.5. It is the exact same, but it's easier to isolate. That's why I use it instead of 1/2. Then I will just add the two velocities, the initial and the final velocity. Okay, the final is that says comes to rest. Okay, to rest. So that tells me that the final velocity is 0. So when you perform this in your calculator, you will get 115.5. Do it right now in your calculator and tell me, did you get the same answer? If you don't get the same answer, you're in big trouble. Okay? If you are not getting the same answer and you don't tell me now, you're in big trouble, because when you're doing the quiz, you will probably commit the same mistake in the calculator. So even though, okay, I do the problems for you, you have your own calculator, try. This is your only tool for the quiz in theory. Okay, so use the calculator. Let me know if you get a different answer than 115.5. Okay, that's nice, Yara. Thank you. So now here there are some isolations. I'm gonna give the isolations to you after. But now you try. A bicyclist accelerates from 5 meters over second to 16 meters over second in 8 seconds. Assuming uniform acceleration, what distance does the bicyclist travel during this time interval? So you're gonna help me with this. When it says from 5 meters over second, what do I mean by that? What kind of data is that? Is it time? Is it initial velocity? Is it final velocity? Is it distance? What is it?
Initial velocity.
So initial velocity, that is right. And then it says 2, 16 meters over second. What is that? Initial or final velocity?
Final velocity.
Remember, 2 represents a final condition and meters per second is velocity. So this is BF, final velocity. And of course, every time we talk about seconds, minutes, years, whatever, that is time. That is never going to change. They're asking you to find the distance. Let me know if you got this answer. This is just about trying, okay? Use the same equation that I projected before. If you kind of forgot, is this one? Okay. Did you get the 84? Yes?
Yes.
That's it, okay? You try, you get the 84, and try to remember how you did it, okay? So what I told you about from and to, remember, I'm giving you this by words. It's not written in the presentation. From means initial condition, and to means a final condition. So if it is not written in your notebook, write it down in a post-it, okay? But do not forget. Do not forget. Now, let's take a look. 2 more equations, velocity and displacement. Yes, displacement again with a longer equation. And under the condition of constant acceleration. You have 2 equations here. I gave you these 2 equations already isolated, okay? It's going to be in Google Classroom. So this is your equation number 4 and number 5. We have seen 5 equations. We have seen 5 equations. I think we're missing, I think, one or two more equations and they're falling objects. So we're in the middle of it. So take a look at this exercise. It says a plane starting at rest at one end of a runway undergoes a uniform acceleration of 4.8 meters per second squared for 15 seconds before takeoff. In part A, you have to find the speed at the takeoff moment and then how long must the runway be for the plane to be able to take off. So with this exercise, I don't know about you. I mean, I do the process here, but I really prefer to do this process in the whiteboard. Now, if you don't want the process in the whiteboard, just let me know. Let's work on this thing. Okay. Bueno. Sorry guys, it's a screenshot that I took you up here and there. So I couldn't see the word problem. That's interesting. So here's the word problem. I'm gonna do my process beside. Okay. So work on it. So let's work with the data first. That's the most important step. So let's see. It says a plane starting at rest. What's the data the problem is giving me in that point? Starting at rest. What does the word rest means in physics?
Zero.
Zero what? Velocity, initial velocity, final velocity, distance, time. Zero what? What means rest?
Initial velocity.
Initial velocity. Initial because it says starting. Okay, so this is telling me an initial condition of the plane. And rest means that it's not moving. So if there is no motion, we say that the velocity in this point is zero. And because we're talking about starting, that is the initial condition of it, we say that this is initial velocity equals zero. That's all I can get for that part. Then it says at one end of a runway undergoes uniform acceleration of 4.8 meters over second squared for 15 seconds. So here it says acceleration of 4.8 meters over second squared. Basically, the problem is telling you that that is the acceleration. Okay, so that is part of the data that you need to highlight. And for how long does it happen? It happened for 15 seconds. So those 15 seconds represent the time. Now the word takeoff significa despegue, okay? So this is the idea of the problem. I'm gonna draw it below. I'm not very good at it, okay? But I'm gonna try. Let's say that is my runway, okay? And I have the plane right here. So initially, we know that it starts at rest. So this gives me an initial velocity of 0 meters per second. We got it from the problem, okay? Then it says that during 15 seconds, the plane is now set in motion. And at the final point, in the final point, which is this one here, it's going to be known as the takeoff, the moment at which the plane is about to be on air, okay? So, what is the problem asking me to find? It says, in part A, it says, what is the speed at the takeoff, okay? So I need to know the velocity in this point, in the point at the takeoff, okay? So this is my unknown. I'm going to call it velocity, final velocity, because this is my initial condition of the plane, and this is the final condition of the plane. Also, the problem is telling me how long must the runway be? No, it's coming. How long must the runway be for the plane to be able to take off? So they're asking me about the runway. They're asking me what is the length the runway should have. Okay, so I need to know the length. The length, or in this case, I'm going to replace the word length by distance. Remember, length, distance, displacement, they both represent the same thing, okay? A change in position. So the plane was initially here, and finally it was there. So a change in position. So what that is the distance. And I'm looking for the distance, and I'm looking for the final velocity. So this is my sketch. What else do I know? I know that during the 15 seconds, the plane traveled with a constant acceleration of 4.8 meters over second square. So maybe this idea of writing the data in the sketch is going to help me. Now you can write the data organized like I did right here, okay? It's okay to do it in any way, but it's good that you have the data organized. And more importantly, that it is correct. So let's see. I have the two equations right there, velocity with constant acceleration and displacement with constant acceleration. So I'm going to work right here. Solution process. So in part A, it says, what is the speed at takeoff? So I'm looking for the final velocity, and very randomly, I have the equation for final velocity that is right there. So it says, the equation says, final velocity equals initial velocity plus acceleration times delta t, or multiply times the time. So the initial velocity, what do we know about the initial velocity? What do we know about the initial velocity? According to the sketch and also the word problem, the plane starts at rest, which means the initial velocity is 0. So when this happens, you are just going to ignore this part of the equation because your initial velocity is 0. So now your equation changes to acceleration times the time. You know the acceleration and you know for how long did it happen. So you say acceleration, that is 4.8 meters over second square, times time. It was during 15 seconds. How much is this? 4.8 times 5. No, 15, sorry. Come on. Uh-huh. How much? 72. So we're looking for final velocity. The unit should be then meters over second. But how do I get the meters over second? Take a look here. These seconds from here are going to be canceled with one of the seconds from the square. Okay? Remember that second square is the same as second times second. Okay? So basically this is the same as having second times second. So the seconds from the top are going to be canceled with one of the seconds below. And in the end, this is what you get. Meters over second. Okay? Those are the only units that you didn't cancel. Meters over second. That is important that you know that. That you know how to cancel the units. Now, in part B, it says, calculate the distance or how long must the runway be for the plane to be able to take off. So I have an equation for displacement right here that says delta x equals initial velocity times delta t plus 1/2. I don't use 1/2, I put 0.5 because it's easier to isolate, plus 0.5 acceleration times delta t raised to the second power. Okay, what do I know about the initial velocity?
It is 0.
It's 0, so you cancel all this term. Why? Because every number that is multiplied by 0 is going to give you 0. So it doesn't matter if you have 0 times 15 seconds, this is going to give you 0 in the end, okay? So what I do is I just ignore the part that has the initial velocity. And now my equation changes. Now is delta x equals 0.5 acceleration delta t raised to the second power. I just plug in the givens and I say 0.5, the acceleration that is 4.8 meters over second raised to the second power times the time that is 15 seconds raised to the second power. Okay, stop ringing. Now let's take a look. Now take a look here what I pointed out. The 15 seconds are raised to the second power. Don't forget that they are raised to the second power. So if you apply that in your calculator, 15 to the second power will give you 225. But also, this unit right here is raised to the second power. So the result of that is going to be 225 seconds raised to the second power. But just the seconds. The number is already in there. like that. I'm just gonna put it like that. Okay, for you to notice the difference of the unit. And here I'm just going to copy this again. Now take a look here. This is what I want you to see. I'm gonna zoom in a little bit for you to see better. Now take a look here. These seconds are what we know as in the top, okay? And these seconds right here. And these seconds right there are in the bottom. So what happens when we are doing conversion factors? What happens when they are in opposite positions? You cancel, okay? So these seconds right here are going to be canceled with these seconds over there. And the remaining unit is going to be only meters. Now, what is the result of that multiplication? What is the result of that multiplication over there?
540.
540, and the unit is meter. The only unit that you didn't cancel. Okay? Okay. Yes. So guys, this kind of equations work like that. Now, yesterday, no. It was the day before yesterday, the class before. People also ask me, Miss, what if we use the other equation? So this is the process, what if? What if you use the other equation that I gave you for delta x? That is equal to 0.5, the addition of the velocities, initial plus final, and multiply times the time. Let's see what happens. What do you think? Is it going to be the same? Yes or no? Both equations are named the same way, are displacement with constant acceleration. Let's see. Do you have initial velocity? Do you have initial velocity? Is it given in the problem? Even if it's zero, it's given, okay? It's not unknown, it's given. So you have this, you have the final velocity, and you have the time. This is what I know as a, like a check-in process, okay? Because this was unknown in the problem. Now I know it. But now I want to see if it makes sense. So I'm going to try with all the data I got. So this is 0.5. This is 0. The final velocity that we got, 72 meters over second, times the 15 seconds. How much do you get from that? You eliminate the seconds over there. How much is that?
The same answer.
The same, right? The same. So this is the other equation that I have. Now, why I didn't use it before? If this equation is a lot simpler. Well, I didn't use it because I don't have the final velocity in the beginning. I don't have the final velocity, okay? The final velocity is what I'm looking for in the beginning. Now, in part B, I could use one equation or the other. In the end, I'm gonna get the same result. Now, what is the condition that you have to see? This one. It says, undergoes uniform acceleration. So that part of that word problem tells you that you can either use displacement with constant acceleration, the long equation or the simple equation. Which one to use according to your guidance? In the beginning, I didn't have my final velocity, so I can't use it. But I can use it in the second step after knowing the final velocity. Now, you can use either way or the other. So you can see that two answers are correct. You can use it as a checking process.